Hello. This is section 2.2 from the James Stewart Calculus Early Transcendentals book. And today we're going to talk about the limit of a function. We're going to go over the various notation and what it means to be the limit of a function. So we have before you an example, f of x equal to x squared minus x plus 1. We have the graph over on the left-hand side, and then we have a table of values on the right. So we want to explore the definition of, or what it means for the limit as x approaches a of f of x equal to L. So, and where these components are, you should be able to, from a graph, identify what the limit of the function is as x approaches L, and also later on in future sections, calculate the limit of a function using various algebraic calculations. So in looking at the table over on the right, you'll notice in the left-hand column the values of x start with 1 and they gradually approach 2 very closely. So if we started with 1 over here and took output values at values of x closer to 2 from the left-hand side, and we would have these function values up on the graph, and we see that they are approaching the value of 4. And on the right-hand side, if we look at this table and we start with 3 and we gradually approach 2 and get really close to 2 from the right-hand side, we're going to be looking at our output values on our graph, and they are also approaching 4. So we define this limit expression, and we say it's the limit as x approaches a of f of x, and we say it's equal to L if we can make the values of our outputs f of x arbitrarily close to L, and as close to L as we like, by taking x sufficiently close to a. Okay, so we're really just taking values that are from the left-hand side and from the right-hand side of a, and really going to the graph and seeing where are the output values tending towards. Okay, so in this case, and our value of L would be this value, and we can calculate that by going over to the right hand or the y-axis and identifying what that output is. All right, so, and also look at these 3 instances of graphs and notice here that in the first instance, a does have an output. We do see that f of a here actually does equal L. We also see that the limit as x approaches a equals L because the output values from both sides of the function approach that function output. In this graph here, f of a, notice that this dot here represents f of a, and let's say that's just going to equal a value of m, but the limit as x approaches a of f of x, if we look at our output values from the left and our output values from the right are approaching L. Good. So we don't necessarily have to have the function output equal to L. We just are looking at the definition of the limit of our outputs that does approach L, but L does not have to be the function output. And in this particular instance, we also see this hole. We don't see any output for A, so we say here that f of A is undefined, or that it does not exist. That backwards E stands for does not exist. So A is not part of the domain of f of x. However, the limit as x approaches a of f of x still equals L because the output values of our graph as x approaches a from the left equal L, and also from the right as x approaches a from the right of f of x also equals L. So we say that the limit in general as x approaches a from either side is going to equal L. Good. So notice here in this example, f of x equal to x squared minus 1. Use a table of values and graph f of x near x equal to 1 and make a conjecture about the value of the limit as x approaches 1 of x squared minus 1 over x minus 1. Now, I can actually just give you foreshadowing and help you calculate a graph pretty quickly if you remember your basic graphs from pre-calculus. We note that f of x is equal to x squared minus 1 over x minus 1. I can simplify that rational function by factoring the numerator and factoring the denominator, which is already prime. I can cancel the x minus 1, and I have that this value is equal, or this function is equivalent to x plus 1 at all points except for x equal to 1. At x equal to 1, that function is undefined by the way that it is expressed. So we can graph but all other values of x, the function has equivalent output. So if we built a table of values, or if we recognize that shape of the graph, we can recognize that as a linear function with x-intercept equal to 1, and we would go up 1 and over 1, and we would have this graph. But for f of x, we would not have an output at x equal to 1 because our denominator would be 0 for that function. So we would go inside and say that this is a whole. Good. So again, just based on what we went over with the graphs above, we can say here that f of 1 does not exist, but the limit as x approaches 1 of f of x, and we see here that that is 2, is going to approach 2 because our function values from either side approach 2. Good. All right. So let's practice with some of these. And also I wanted to note some notation. So notice here one-sided limits versus two-sided limits so that we can practice with some examples. Notice here that this expression has an extra sign right after the A. Okay, we call that, and we say that this is the limit of f of x as x approaches A from the left. So if it's from the left, this is the left of A, right? And this is the right of A. Good, so we're looking at values that are approaching from the left. Good, and so we're only interested in what function outputs are approaching A from the left. Good, so notice, and we put that minus and the pluses, as you'll see for right-handed limits down below. This is limit as x approaches A from the right. We put those plus and minus signs in the exponent arena because we usually reserve plus and minus on the left-hand side of A for the actual positive or negative sign. Good, so, and just to be clear, the limit as x approaches A of f of x equal to L is a two-sided limit. And we must consider both sides for the limit to exist. And we'll clarify that in a moment. Any limit that exists, we say that that limit is actually a finite real number. Okay. But with one-sided limits, we only are concerned with the shape of the graph or the graph outputs from that side. Good. All right. So this is how we really define our limit as x approaches a from both sides, our two-sided limit. We say that the limit as x approaches a of f of x is going to equal a finite number, equal L, if and only if the limit as x approaches a from the left equals L and the limit from the right equals L. Okay, sometimes it might not exist. So I give an example here, just giving 3 graphs right down here as examples. Okay, maybe I don't need 3 examples, but in this case, if I said, right, if this were my function, and this were 1, and this were minus 1, we can see here that f of 0, because this is the value of 0, f of 0 does equal minus 1. We would say that the limit as x approaches 0 from the left of f of x is going to equal 1 because the outputs from the left-hand side are approaching the value of 1. We say that the limit as x approaches 0 from the right of f of x is going to equal negative 1, right? So because the function outputs are approaching negative 1 from the right, we do see that f of 0 does equal negative 1 because that's where we have a solid dot and not a hole. It is a function because it passes the vertical line test, but we notice also that the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. So the limit as x approaches 0 of f of x does not exist. Good. And here, if we had, again, if this were 1 and this is 2, say, we would say that f of 2 does not exist, but the limit as x approaches 2 from the left of f of x does equal 1 because the outputs are tending towards 1. The limit as x approaches 2 from the right of f of x, so we're taking values that are getting closer to 2 from the right, and we're looking at our function outputs. They also equal 1, and so we can say that the limit, because the limit as x approaches 2 from both sides equals the same value, it does equal 1. Good. So let's take a look at some of these examples. Use the graph of g to determine the following values. So we see for g equal to 2, or g of 2, for x equal to 2 here, we see a solid line or a solid dot output there. And looking at our graph, we see that this is going to equal 1. The limit as x approaches 2 from the left, we're looking at output values from the left, right? And that from the left, we see that our output here is going to equal 4. We see the limit as x approaches 2 from the right. So this is x approaching 2 from the right. And we see that that output is going to equal 1. But our two-sided limit is not going to exist because the limit as x approaches 2 from the left equals 4, which does not equal 1, which is the limit as x approaches 2 from the right. And so the limit does not exist from both sides, for the two-sided limit. Helpful? I think that does it. And that concludes just the basic ideas of the limit of a function and understanding the notation of what you are looking at. We will move forward with section 2.3 and even beyond and discuss more ways to calculate limits.